The title of the chapter is Requirement Analysis. So again, this is from Kosyakov. And this is the agenda, which follows the format that they have provided in the textbook. So 7 points that we want to address. First, developing the system requirements, requirement development and sources, features and attributes, the actual development process, the hierarchy, the metrics, and then finally, the verification and validation. So we'll start with developing these system requirements. So we provided some background on that already. This is to complement our initial discussion. So we already went through this process of formulating our problem. So that was part of the process of the needs analysis, which is intended to provide a well-documented documentation for the justification of the beginning of this new development. So that process typically produces a set of operational requirements or the objectives that this system is trying to address, and also describe what the new system must be designed to do. Okay, so from that objective perspective, these are the things that we hope our system is able to accomplish. And we call those operational requirements. The principal objective of the concept exploration, which is the next phase, is to convert these operationally oriented requirements or objectives of the system into an engineering-oriented version of requirements. This conversion is necessary to provide an explicit and quantifiable basis for selecting an acceptable functional and physical system concept. So we are trying to go now from this vision. We understand the problem. These are the things that are objectives for this system based on our understanding of the problem. So now we want to take those operational requirements and we want to make them more engineering oriented, basically providing them with some type of quantifiable basis so we can have some way of verifying and validating those requirements. So we are now moving from the needs analysis to the concept exploration. And as you can see for the output, we have the system performance requirements and also candidate system concepts, right? So from this process, we hope to have at least a group of concepts that we are going to evaluate so we can decide later which one is the one that is going to be more efficient for our goals. So the focus is on the development of performance requirements that accurately state the customer's needs. So if you remember that materialization status, that table that I showed you at the beginning, we are now moving from this needs analysis phase to the concept exploration phase. Here's when we start with a vision based generally on the above feasible concept that is coming from this needs analysis. So we are moving now to this second part of the materialization of the concept. So if you remember, we have the different levels for our hierarchy. So now we are not only focused on the system level or the general level, high level design, we are now going deeper into actually defining requirements for the subsystem and maybe start visualizing what are the components and subcomponents that are going to be used to develop these concepts. So the activities in the concept exploration phase and their interrelationships are the result of the application of the systems engineering method. So you should, by now, have a good idea what the systems engineering method is. So those 4 steps. So what we have here is just a discussion on how those systems engineering method steps are applied to this concept exploration. So we start with the requirement analysis. So some of the activities are analyzing the stated operational requirements in terms of their objectives. So what are the objectives of our system and restating it or amplifying those to provide specificity, independence, consistency. So as we already mentioned, we want to be more specific in the sense of providing maybe some quantifiable measurements to some of those requirements. In terms of the functional definition, the performance requirement formulation, this is translating operational requirements into system and subsystem functions. So that's what we are illustrating here in this materialization, right? So we are looking at the subsystem level, not only at the high level, but going deeper. And formulating the performance parameters required to meet the stated operational requirements. So what are those metrics that we are going to use to measure the performance of our system? Is it going to be based on the number of people that we can serve? This is going to be based on the cost associated with the operational status. It's going to be based on the technology that we are going to be applying. So what are those performance parameters? Going into the physical definition, the actual implementation, we are going to start looking at different technologies that could be used to achieve our objectives. Specifically, you have a visualization of our subsystems. How are we going to be building those subsystems in terms of technologies? Developing those functional descriptions, which is something that we already discussed, right? So from this problem definition, we take what are the functions that we need to perform in order to achieve a solution for this problem. And from that functional description, we can start visualizing different subsystems and identify system components for the most promising cases. And going back to the performance characterization, defining a necessary and sufficient set of performance characteristics reflecting the functions essential to meeting the system operational requirements. And then for the validation part, this includes conducting analysis to define a set of performance requirements. So, and validating the conformity of these requirements with the stated operational objectives and refining the requirements if necessary. So, in terms of defining these requirements, how are those connected to our operational or objectives for the system, and making sure that those requirements are addressing each one of those objectives, and somehow you have defined requirements addressing each one of them. The interrelationships among the activities in the above steps in the systems engineering method are depicted in this figure, which is similar to what we saw for the needs analysis. So if you want to get a good understanding of the concept exploration and the systems engineering implementation within the concept exploration, this is a good summary of what we just discussed. So you see all 4 steps are represented by each one of those levels. So operational requirement analysis, performance requirement formulation, implementation, and performance requirement validation. Okay, so that's how we get started. We try to visualize from the operational or these objectives that we want to address for our system or the problem that we are trying to address. We start looking at refining those, start developing these performance system requirements, and then based on that, we follow the systems engineering method to make sure that those are complete. Move to the next step. Here we look at requirements development and sources. So these requirements can come up from different sources. There's 4 general approaches that we can try. So the first one is from a development point of view of a new system to operate in a future environment, like that example that I discussed for the progress report, right? That potential environment or artificial environment to live in Mars or outside the Earth, right? That's a future environment that will be based on new technology mostly. These requirement sources might include visionaries or cutting-edge researchers that are both inventing capabilities and discovering them. So those are, I mean, not necessarily as typical, but those can happen. Improvement type of development is given the existing system, consumer demands, can identify new ways to improve the existing system. So those are other areas that you can start looking at. Threat driven, right? So like that doesn't need to be like enemy in terms of wars, but it could be something like a virus, right? So you have a risk associated with some type of virus. So you are forced to create this new technology to try to make sure that that is controlled. So new threats require a re-examination of existing system and concepts with improvement to counter these threats. In addition, new allied or complementary systems are introduced, enhancing the original system, but requires a new way to interface and operate. So if you're familiar with, for example, digital twins, the Industry 4.0, this is a new type of vision for conducting manufacturing in which you are keeping your real system, but you're building like a digital twin. These are complementary systems that can help you be more efficient, right? And these addition can generate some new ways of enhancing the original system, but requires new ways for interfacing with the original system and to operate. So these are 4 general approaches that can help you originate those requirements. Okay, so in terms of features and attributes, a feature is a set of requirements that will satisfy an objective. So basically, this is like a group based on your requirements. This feature is satisfying this objective, which is typically at a higher level of abstraction. So for example, a vehicle that can support travel, soccer game support. This is a very general description, right? And this can be, I mean, just from this high level type of requirement, you might think about a minivan, but there can be a lot of different vehicles that can satisfy this, this requirement. Could be an SUV, or it could be a truck, it could be a school bus, an ambulance, right? Because there's no necessarily a very specific description of what you are trying to achieve. So this feature may be composed of the following requirements, right? So you have that high level requirement, and then you have additional requirements. The vehicle can transport a minimum of 6 school-age children. Vehicle can transport a minimum of 10 soccer balls, 20 jerseys, and 2 games worth of snacks. Vehicle can transport a minimum of 2 full-size coolers and of food and beverages. So now these additional requirements can give you a better perspective of what you're looking for. So again, you have that feature, which is a requirement that is set to satisfy an objective, but it's a higher level, right? Like the example, and that feature can be composed of multiple requirements. These vary between requirements, users, and their system needs. It's useful to organize a set of requirements to describe the performance to a set of specific users. So again, if you're targeting different type of customers, this could be a good way to separate these requirements. So this group of requirements, this feature is more addressing the needs of this group of customers and so on. Collection of features developed to ensure that the proper set of stakeholders have been adequately consulted to satisfy their specific needs. So you have a collection of features that are addressing, let's say you have multiple customers that are expected to use your system. So there are specific features that are linked to those customers. Requirement attributes describe the technical composition of the requirement. Like it is measurable, is it quantifiable, under what conditions, and qualifier is the system satisfied. So to define these system requirement attributes, often the SMART approach will accompany requirements. So SMART stands for simple, measurable, attainable, realistic, and time-bound, right? So while you're defining your requirements, this is a good approach to keep in mind. The requirement must be simple, measurable, attainable, realistic, and somehow time-bound. These attributes can determine whether the requirement is well-written and stands a chance of accurately representing the system capability. So here's some examples of good requirements. The system shall be able to transport up to 20 passengers within a radius of 50 miles. All right, so that shows some simple, measurable, attainable, realistic, and time-bound. Maybe time is not very specific here, but you know it's a travel distance that is realistic. So it will involve some limitations in terms of time. Why is this good? It provides a measurable amount of passengers, an operational radius, so the transportation system can be tested to see if it meets the requirement. Another requirement, the system shall provide a means of combination between the transport and the dispatch station to exchange health and status data of the transport system, exchange every 15 minutes. So this is a very long requirement for my taste, but still provides some of the pieces that are associated with this SMART approach. Quantifiable means of describing the needed information to be exchanged. Also provide the time bound, is realistic, attainable, and simple. Example of pull requirements, the system shall be able to operate in all weather. So you can see why that is that poor based on that approach, right? There's no way to quantify this. Stated all weather implies that every imaginable weather condition will need to be satisfied for the transportation system. Another example of a bad requirement, the system shall be diesel power. Why is this poor? State the design by using a diesel engine. So it's providing a solution instead of stating the requirement. How do we know this is the correct solution? As there's maybe other alternatives. Should requirements should describe what needs to occur, not how it should be built. So this is something that I saw in some of your descriptions. I was stated solution must not be present. That could be a concept, an alternative. But remember, when you're expressing your problem, your requirements, you are not stating the solution. Same thing, the system shall use Volvo engines. That is presupposed the solution as well. So you can see the difference between good requirements and poor requirements. Any questions? So even though it's following the format that we discussed, right? They're using the shall, stating the requirement in such a way, they are not necessarily good requirements. Okay, the requirement development process. So here's the picture that shows the general process for development requirements. So you go from the elicitation, you start studying that problem or that situation that is exposed, and then you start documenting and providing ways to validate the requirements. All of that combined goes to this requirement documentation. And as you look into how realistic and how quantifiable those requirements are, you might need to go and iterate back to the requirement analysis until you get the right description. So the first activity involves the creation of a set of requirements. In the concept exploration phase, a set of operational needs and requirement has been established. This must be translated into a set of system-specific requirements describing its performance. So from here, we move to the requirements elicitation. So when analysts are developing operational requirements, they rely heavily on input from users and operators, typically through market surveys and interviews. So again, this is part of the needs analysis. So when you're getting into the operational requirements, these are more like the objectives that the system must accomplish. When the analysts are developing the performance requirements, they rely on both people and studies. Initially, the customer is able to provide threshold of affordability and levels of performance that are desirable, but subject matter experts can also provide performance parameters as a function of technology levels, cost, and manufacturability. A useful approach to developing requirements of any type is to ask the 6 interrogative: who, what, where, why, when, and how. The operational requirements, which is again at the needs analysis phase, objectives, focus on the why. Why do we need this? Why do we need to solve this? Defining the objectives of purpose of the system. The performance requirements focus on the what, defining what the system should do and how well the system must accomplish that. Okay, so why do we need the system? What is the problem that we are trying to address? That's part of the needs analysis. That's in the problem definition. You're able to come up with these objectives that are the operational requirements. And then based on that, we start refining those in the concept exploration. We start looking at what the system should do and how well. This activity start with the initial set of requirements from the elicitation stage. Individual requirements as well as the set of whole are analyzed for various attributes and characteristics. Some characteristics are desirable, such as feasible and verifiable. Other characteristics are not, such as vague or inconsistent. So for each requirement, a set of tests or questions is applied to determine whether the requirement is valid. These tests are specific to the development of system performance requirements. So the first question is the requirement traceable to a user need or operational requirements? Can you link these requirements, these performance requirements, to one of the objectives of your system? Is the requirement redundant? Is there any other requirement overlapping this one or canceling this one? Is the requirement consistent with other requirements? Again, requirements should not contradict each other or force the engineer to an infeasible solution. Like by satisfying this one, I would not satisfy this one. So that contradictory set of requirements cannot coexist. So these are 3 questions that you might need to ask as you build your set of performance requirements. And you remember those 6 different type of requirements, those are all of them performance requirements. Is the requirement unambiguous and not subject to interpretation? Is the requirement technologically feasible? Is the requirement affordable? So now we're getting into cost, performance, and if it is a way for you to verify that the requirement is accomplished. If the answer to any of these questions is no, then the requirement needs to be revised and most likely omitted. In addition, other requirements may need to be revised after performing this test. So this is an iterative process. So as you revise one, that might lead you to another revision for the other requirements. We good? Very good.
So the first one, are they traceable?
This one?
Yeah, are they traceable to operational?
Yes. Okay. So in addition to individual requirement tests, a test that you are going to be performing to each individual requirement, a collective set of tests is also performed, usually after the individual tests have been performed. So let's say you have a group of components that have their separate requirements, they're meeting those requirements, but then when you put them together, they will have to perform from another perspective, I guess, from another point of view, another performance metric. So you might need to provide a test for those requirements as a group. So does the set of requirements cover all of the user needs and operational requirements? Is the set of requirements feasible in terms of cost, schedule, and technology? And can the set of requirements be verified as a whole? Both type of tests may need to be iterated before a final set of performance requirement exists. Okay, so again, a lot of iterations here. We are going from understanding our problem, defining the needs, to establish some objectives. And now those objectives are guiding us. Those objectives are connected to those functions that we identify initially, that the system must perform in order to achieve our goals. So now that we have those operational requirements, we are trying to go deeper and make those more specific in terms of technology, in terms of engineering. So we are trying to provide some type of quantifiable metric. In most of them, we're following the SMART structure, simple, right? But at the same time, satisfying the rest of the conditions. And then we are providing some additional strategies here to test whether or not the requirements are complete as individually defined or as a group. And then here we have, I'm not going to go through this. I put this example there for you to read on your own. But this is a very detailed example that talks about a jet-powered aircraft. And this is a good example for the concept exploration, the acquisition of these new commercial aircraft. So I encourage you to read through this, and it's also available in your textbook. Questions? Okay, so now we're moving into the hierarchy of requirements. So these requirements are organized into several levels to assist the requirements engineer and means to develop the requirements for the proper scope. So we organize the requirements into operational, system, performance, and components. Each requirement level can provide information to different users as well as guide the system and concept development. So operational, system, performance, and components. Operational described by what needs to execute within the scope of operations. These requirements are generally less quantified and higher level. Users and stakeholders' perspective play a larger role in shaping these requirements. So again, these are coming from the needs analysis when we are defining the problem, and must initially be described in terms of operational outcomes rather than system performance. Since the initially stated operational requirements for a new system are seldom based on an exhaustive analysis, these requirements will be refined during the development process as further knowledge is gained concerning the system needs and operational environment. Okay, so again, this is like when you are, you have a problem, right? Let's say any problem that you might face, okay, I have this problem at hand. These are the things that I need to accomplish in order to solve the problem. But then in order to accomplish those things, you have a set of things that needs to happen. So for example, you decided master students that are coming internationally, I want to go do a master in engineering in the United States. That's your goal, right? So what are the things, what are the other things that needs to happen in order to you to get to that point? So deciding the university, applying to university, if you get accepted, are you going to evaluate different offers, which one you're going to pick? Okay, next, how are you going to decide what to move, when to move, where are you going to live, and so on. So a lot of things that needs to happen, that needs to be defined in order for you to get to that last goal. So that's what we are trying to illustrate. So those operational requirements is basically defining the goal, like this high level, this is what I want to accomplish. But then in order to accomplish that, you have to go deeper and define those system level requirements, focus on the system and how it performs in the operational environment, concerned with the supporting infrastructure as well as other systems that it may come into contact with during the expected operations. Focus more on quantitative metrics and how the system will perform within the environment. And different perspective may be garnered from using a context diagrams or other ways. So those context diagrams that we define initially, helpful to look at the system in a holistic manner in order to ensure completeness with the requirements. In terms of performance level requirements, in deriving this group of requirements from the operational objectives, it is first necessary to identify the major functions that the system must perform to carry out the prescribed operational actions. So for example, let's say a system is needed to transport passengers to such destinations as they may wish along existing roadways. So again, if you look at a solution, you start thinking maybe a train or subway or a bus system. We don't want to specify a solution, right? We want to specify what's needed to accomplish that. There needs a source of power, a structure to house the passengers, a power transmitter interface with the roadway, and operator activated controls of locomotion and direction. So those are functional elements that might be needed in order to accomplish that system. Expressed in functional terms, like verb and object, these elements may be called power vehicle, house passengers, transmit power to roadway, control locomotion, and control direction. So these are the functions that my system must perform. A beginning, this process has already been made in the preceding phase. However, a more definitive process is needed to establish specific performance parameters. During this phase, the functional definition needs to be carried a step further to a definition of subsystem functions and to the visualization of the functional and associated physical components, which collectively can provide these subsystem functions. So as I stated, we did part of it in the needs analysis phase. Now we need to revisit those functions. They need to carry out a step further, maybe looking into the function that each subsystem must perform now, and how is that going to be working with the existing technology. The non-deterministic nature of system development, derivation of performance requirements from desired operational outcome is far from straightforward. So this is not simple. In going from the more general operational requirements to the more specifically defining system performance requirements is necessary to fill in many details that were not explicitly called out in the operational requirements. This can be done in a variety of ways, meaning that more than one system configuration can satisfy a given set of system requirements. And that's what we want. We want to come up with different concepts that we can evaluate to choose the best. This is also why in the system development process, the selection of the best system design at a given level of materialization is accomplished by trade-off analysis using a predefined set of evaluation criteria. Okay, so best system, not optimal, best, the one that meets those trade-offs the best way. So for example, in designing a new car to achieve an operational goal of 600 miles on a tank of gasoline, one could presumably make its engine extremely efficient, or give it a very large gasoline tank, or make the body very light, or some combination of these characteristics. All this, somehow, if you do it right, can get you to that goal of 600 miles on a tank. It didn't state how big the tank has to be, right? So you can make it huge and get it to that level. Which combination of these design approaches is selected will depend on the introduction of other factors such as the cost, the risk, passenger capacity, safety, and many others. But that gives you the flexibility to evaluate different concepts. There is no direct method of inferring a corresponding unique set of system performance characteristics that are necessary and sufficient to specify the requirements for a system to satisfy the operational needs. So basically, there's no a perfect recipe to say, based on these operational requirements or the objectives, this is the exact number of requirements that will be needed. That doesn't exist. We might rely on experience-based heuristic and to a large extent, a trial and error approach. Every development will be different unless you have somehow, let's say you're working with airplanes and you have worked with developing new airplanes for many, many years. So there may be some type of experience-based heuristic. This is what we are referring to. Based on the experience, because you have gone through similar processes, you know what to do, you know what to expect, you know how much requirements will be needed. But most of the time, you are based on trial and error. This is accomplished through a process in which a variety of different system configurations are defined. The performance characteristics are deduced by analysis or data collection. And these are subject to effectiveness analysis to establish those characteristics required to meet the operational requirements. Then we get to the component level requirements and specifications. These are more focusing on the technical aspect of the system at a lower level of technical detail. It might also be concerned with the design. These are highly quantitative in nature and will come with some expected performance. Specifications are developed as the next steps from the component level requirements and to guide manufacturers with desired level performance and precision while constructing these components. So in terms of analysis of the stated performance requirements, in the concept definition phase is especially important because these requirements, as initially stated, often represent an imperfect interpretation of the user's actual needs. The task of understanding the source of the given performance requirements in terms of user needs is the particular province of systems engineering. So again, we are transitioning from this general high-level understanding of the problem to a very specific engineer type of design. This task requires an intimate acquaintance with the operational environment and with system users as circumstances may permit. In the case of complex operational systems such an understanding can best be derived through years of work in the field, as I stated already with the airplane example. Categories of system requirements. Attention is usually focused on what functions the system must perform and how well. We have named this type of well-defined requirements as functional and performance. There are, however, other type of requirements that may be much poorly defined or even omitted in this phase. This includes compatibility requirements, reliability, maintainability, and availability requirements, and also environmental requirements. In terms of life cycle scenarios, to understand all the situations that the system will encounter during its lifetime, it is necessary to develop a model or scenario that will identify all of the different circumstances to which the system will be exposed. This will include at least storage, transportation, assembly, deployment, operation, maintenance, modification or upgrading, and finally, disposition. So all systems will go through these at least these 8 scenarios. The model of these phases of the system's use must be sufficiently detailed to reveal any interaction between the system and its environment that will affect its design. So for example, the maintenance of the system will require a supply of spare parts, special test equipment, special test point, and other provisions that need to be recognized. Only by visualizing the complete life of the projected system can valid requirements and associated costs be developed. So if you don't take into account, let's say, well, what I'm trying to say is that if you don't take into account what will happen when you're performing maintenance, then you might miss out some of the requirements that are needed for your design. Okay. So requirements metrics, these are used to inform the analyst or the decision maker whether or not the system will accomplish its intended objective. Test engineers will use metrics to evaluate whether the test on the selected system was successful or not. And 2 commonly used measurements are used, which are listed here: measures of effectiveness, or MOEs, and measures of performance, MOPs. And those are terms that are commonly used in industry. MOEs refers to a qualitative or quantitative metric of a system overall performance that indicates the degree to which it achieves its objective under specified conditions. And MOE always refer to the system as a whole. So how close were you to this performance? How far you were about this performance and so on. An MOP refers to a quantitative metric of a system characteristic or performance of a particular attribute or subsystem. MOP typically measures the level of physical performance below of the system as a whole. So you're looking at a specific area of the system for this type of performance. So again, difference between MOE and MOP. MOE looks at the high level as a system as a whole. MOP is on specific areas of the system. An MOE or MOP will have 3 parts: the metrics, its units, and the conditions or context under which the metrics apply. So for example, an MOE of a new recreational aircraft will be maximum range in nautical miles at sea level on a standard atmospheric day. Okay, so those 3 areas are, those 3 parts are accomplished. MOE is at the system as a whole level. So this is looking at nautical miles. The metric is maximum range. The units are nautical miles, and the conditions are standard atmospheric day. This MOE relates to the aircraft as a whole and describes one aspect of its performance in achieving the objective of an air flight. One more thing, which is verification and validation. Performance requirements validation involve 2 interrelated activities. First one is integration of requirements derived from alternative system concepts. And 2 are effectiveness analysis to demonstrate satisfaction of the operational requirements. Okay, so those are the two activities that we had to perform for validation. Performance requirements are defined in a living document. Requirements are reviewed and updated through the system lifecycle. So a living document means that is a document that is not completed until the process or the development has been finished. So it will go through multiple iterations. And that's it.